In this video, we're going to practice drawing the Lewis structures of these three polyatomic ions, and we're going to be calculating formal charge as a way of evaluating the Lewis structures that we have drawn to determine whether or not they're accurate. So let's start with cyanide Cn minus and its Lewis structure. Carbon has 4 valence electrons, nitrogen has 5 valence electrons, and remember when we're drawing the Lewis structure, we have to add an electron for every negative charge. So this polyatomic ion has a total of 10 valence electrons. Again, 4 valence electrons for carbon, 5 for nitrogen, and then 1 extra electron because of that negative charge. We don't have any central atoms in this molecule. We just have 2 atoms, the carbon and the nitrogen. Putting them together with a single bond leaves us with 8 electrons to work with. Even though we don't have an inner and an outer atom, normally we would start by putting the octets around the outer atoms, but we don't have an outer atom, so let's just start by putting the octet around carbon because it's on the left. So carbon has 2 electrons currently, and we need to give it 6 more to get to its octet, which leaves us with 2 electrons remaining. Nitrogen only has 2 electrons. It does need to have more electrons, but we only have 2 to give it. So if we're just looking at if we're just simply looking at octets, for carbon, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons, so we're good there. For the nitrogen, we have 1, 2, 3, 4. Nitrogen needs more electrons. We know what we need to do here. We're going to take one of the lone pairs on the carbon and turn that into a double bond. Now nitrogen has 1, 2, 3, 4, 5, 6, so we need to do that again. Take another lone pair from carbon and turn that into another bond. And so where does that leave us? Let's take a look at our formal charges. Carbon atom, its formal charge is calculated by taking the valence electrons minus the number of bonds, which is 3, minus the number of non-bonding electrons, which is -1. So this carbon atom has a formal charge of -1. And then what about the nitrogen? Nitrogen's formal charge, nitrogen has 5 valence electrons. This nitrogen also has 3 bonds and 2 non-bonding electrons. So that gives it a formal charge of 0. Now, I have mentioned in previous videos that the sum of all the formal charges, so in this case -1 plus 0, that has to add up to the overall charge, which in this case it does. The overall charge of this, I did forget to write that when I drew the Lewis structure, the overall charge is a -1, so our formal charges are adding up to the correct number. And these formal charges look pretty good. We do have small formal charges, a 0 and a -1. The only thing that we have to really ask ourselves is this the best place for the negative formal charge, or would it be better suited if it was over here on the nitrogen? And the only way for us to evaluate that is to just kind of think along the lines of a negative formal charge does mean that there are too many electrons around this carbon. So the way that we would get rid of this negative formal charge would be by taking the lone pair away and creating another bond. Now, in doing that, if we do that, we do fix the formal charge on the carbon. Carbon now has a formal charge of 4 minus 0. So in terms of formal charge, carbon's looking good. But look at what we just did to nitrogen. Nitrogen now has 2, 4, 6, 8, 10 electrons around it. Oh my gosh. We're not allowed to do that. Don't do that. Cannot give nitrogen more than 8 electrons. So in this case, even though the formal charge is not necessarily in the best spot, it is the only place that it can go. We can't fix that. So this is the best Lewis structure for cyanide. And let's move on to our next example, H3O plus hydronium. Calculating the number of valence electrons, we have 3 hydrogen atoms. Each hydrogen atom has 1 valence electron. And we also have one oxygen atom. The oxygen atom has 6 valence electrons, and we have a positive charge, which means that we are deficient by 1 electron. We're short 1. So 3 times 1 is 3, plus 6 is 9, minus 1, we have 8 electrons to work with. Now, in terms of putting these atoms together, remember I have told you that the first atom in the formula, as you read from left to right, is always going to be your central atom unless the first atom is hydrogen. If the first atom is hydrogen, ignore it and move on to the second atom. So that means oxygen is our second, is our central atom, and our 3 hydrogens are arranged around the oxygen. Connect those outer atoms to the oxygen with single bonds, which uses 6 electrons, 2 per bond, 2, 4, 6, and we have 2 electrons left. We want to start by working on the outer atoms. They should each have octets, except these are hydrogens, which only want 2. So all of our hydrogen atoms are happy with their 2 electrons, and now we move to the inner electron, the inner atom. It has 2, 4, 6 electrons. It needs 2 more, and we have 2 more to give it. So here we have used up all of our electrons, and we are now ready to calculate the formal charges of all the atoms to check our work. All of the hydrogens are exactly the same in terms of their bonding environment, so I'm going to calculate the formal charge of this hydrogen, and we know that it's going to be exactly the same as the formal charges of the other 2 hydrogens as well. 1 valence electron for that hydrogen minus 1 bond and non-bonding electrons, 0. So that's a formal charge of 0 for all of these hydrogens, which means that they are all good. For the oxygen in the middle, we have 6 valence electrons. For an oxygen, we have 1, 2, 3 bonds around that oxygen, and we have 2 non-bonding electrons right here. That gives us a formal charge of +1, which I'm going to write that right there. Remember, we draw a circle around it to make it easy to see. And this is what we've got. As far as the sum of the formal charges, they should all add up to +1. So a 0 plus 0 plus 0 plus 1 equals +1. So we're good in that regard. Putting a positive charge on an electronegative atom like oxygen isn't necessarily that great. When we see a positive formal charge, we know that that means that the atom wants more electrons, but we don't have any more electrons to give it. We can't take one of the bonds and turn it into a lone pair. Let's just imagine what it would look like if we did that. So if we took that bond and turned it into a lone pair, what did we just do? We just broke that hydrogen loose. So we don't have anything to give that oxygen. This is the best Lewis structure that we can draw for this molecule. Even though we do have a positive formal charge on there, there is no way to get rid of it. So now here we are at our last example. Look at this beautiful molecule. It looks kind of complicated. Let's start by adding up our valence electrons. We have 2 carbon atoms in the formula. They each have 4 valence electrons. We have 3 hydrogen atoms. They each have 1. We have 2 oxygen atoms. They each have 6. And then we have that -1 charge that gives us 1 extra electron. So this is 8 plus 3 is 11 plus 12 is 23 plus 1 is a total of 24 electrons. Now the structure for this is a little bit tricky to read from the formula, so I'm going to give you some hints. In this formula, the 2 carbon atoms are bonded directly to each other, so we're going to draw it like that. And then the carbon on the left hand of our drawing, we're going to give that guy all 3 of the hydrogens, and the other carbon will get the 2 oxygens. So this is kind of the skeleton that we're going to start with. And putting those atoms together, we used 2, 4, 6, 8, 10, 12 of our electrons. So let's subtract that, and we have 12 more to go. Let's work on our outer atoms, and we're going to define the outer atoms as the hydrogens and the oxygen. So the hydrogens each want to have 2 electrons, and they all do have 2 electrons, so all of our hydrogens are happy. Our oxygens do want an octet. Starting with the oxygen on the top, it has 2 electrons, so it needs 6 more, and that brings us down to 6 remaining electrons. And this oxygen also, it has 2 and it needs 6 more, which then uses up all of our electrons, leaves us with 0. Now let's focus on our inner atoms, the carbon atoms. So this carbon right here, it has 2, 4, 6, 8. It has its octet. This one has 2, 4, 6. It needs 2 more. So we know what to do. We're going to pick a lone pair from either one of these oxygen. I'm just going to choose this one right here, and we're going to make a double bond in between that oxygen and the carbon, and now everybody has an octet. The last step here is to calculate formal charges to check our work. All of the hydrogens are identical. 1 valence electron minus 1 bond and no non-bonding electrons is a formal charge of 0. This carbon atom, now the 2 carbon atoms are not identical. They don't have the exact same bonding environment, 4 single bonds versus 2 single bonds and a double bond. So we have to calculate the carbons separately. 4 valence electrons for the carbon minus 4 bonds and 0 non-bonding. So that's another formal charge of 0. So far we're looking good. Let's do this oxygen right here. Also, the 2 oxygens are not identical, so they each have to be calculated one at a time. Oxygen has 6 valence electrons. This oxygen has 1 bond and 6 non-bonding, so that's a minus 1 formal charge. We'll write that one down. This carbon atom has 4 valence electrons. It has 1, 2, 3, 4 bonds, no non-bonding, so that's another formal charge of 0. And our last oxygen atom, 6 valence electrons, 2 bonds, and 1, 2, 3, 4 non-bonding is another formal charge of 0. So first thing we should check is, does the formal charges sum up to the overall charge, which it does, a -1 and a -1. Then the next thing that we should look at is there any way to get rid of this? Well, obviously there isn't, because the compound has a negative charge, which means we have to have a negative formal charge somewhere. But let's just imagine we weren't sure if this was the best place to put it. So if we wanted to put this formal charge somewhere else, if we wanted to deal with it, what we could do is take some electrons away from that oxygen by creating a double bond in between the oxygen and the carbon. And if we did that, this oxygen would now have a formal charge of 0, but what have we done to the carbon? Carbon now has 2, 4, 6, 8, 10 electrons around it, which is no good. So don't do that. It looks like this is the best spot for this formal charge.